Welcome everyone. You are joining us for Precision Automation Principles for the Optimal Testing and Packaging of PIC Devices. This webinar is presented by Aerotech and hosted by Photonics Media. Today you're going to hear from Brett Heintz. He is an applications engineer at Aerotech, focusing on the technical challenges associated with the design, production, and programming of precision automation systems for optoelectronic packaging and testing. In this session, he provides a guide for selecting precision motion equipment to minimize the impact of positioning errors on optical alignment test results. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during this event, please log out and back in to rejoin. You will be able to access a recording of this online after the webinar, and you will receive a link to that recording in your email inbox. So with nothing further from me, I'd like to welcome Brett Heintz. Welcome.
As you said, my name is Brett Heintz. I'm an applications engineer at Aerotech Inc. I focus on optical alignment and silicon photonics type applications and helping our customers to enable and automate their processes. Today we're going to talk about precision automation principles for testing and packaging of silicon photonic devices and similar devices. Out of this presentation, I hope to do a couple things. One, we'll talk about the principles so that you understand where we're coming from and so that you understand some of the technical terms that I'm using. And my goal is to get you to a point where you're able to identify a couple of the key specifications that you'll need to talk about with precision automation suppliers in order to successfully automate the process. These photos are courtesy of Photonics. You'll see on the left-hand side here, we have a die that's an active die that's being probed. And when you do this sort of probing on silicon photonics, it typically requires a high level of precision automation. Not only does it require many different axes of motion, but it also requires a significant number of different types of complex programming like optical alignment algorithms and virtual pivot points, things of that nature. So what you're seeing on the left-hand side with that die, there are 4 axes beneath the die itself, X, Y, Z, and theta axes to position the die underneath the RF probes. And then there is an optical array, and that array is connected to a 6 degree of freedom, high precision optical aligner. We've seen a trend recently in a lot of different customers who want to move to edge level coupling at the wafer level, specifically in trenches that span or traverse the wafer itself. These are particularly challenging, especially when you're moving from surface coupling type applications to edge coupling type applications at the wafer level. So we're going to talk later in this presentation about the different types of specifications that are important for that. First, before we get to that, I want to talk about precision motion specs in general and the different types of terminology that you need to know in order to choose a system that will make your application successful. So the first thing you'll note is anytime you go to a precision motion supplier's website, you'll likely see tables such as these, tables with various accuracy, repeatability, and similar types of specifications. It's important to know that there's not one standard or universal standard from supplier to supplier. So when you're comparing specs from one supplier to another supplier, you have to be very cognizant about what the differences in the testing requirements are, what the differences in the environment are, and so on. Even if you're looking at specs from a single supplier, there's differences, and this is what this slide is illustrating. So if you look at the table on the left-hand side, you'll see a slide showing single axis motion specs from one of our Aerotech stages. And if you look at the spec table on the right-hand slide, this shows various specs from the same stages, but stacked up into a multi-axis system. So if you look at a particular spec, like let's say the bidirectional repeatability, on the left-hand side, you'll see plus or minus 75 nanometers. On the right-hand side, you'll see things like plus or minus 150 nanometers, plus or minus 175 nanometers. With the same stage, we have almost 2 times and more the bidirectional repeatability specified. This is the point, is that we're illustrating that you need to understand the differences in testing conditions. We've tested the stages in the same environment. However, on the left-hand side, we've tested them as a single axis at the tabletop, and on the right-hand side, we've tested them as a multi-axis stack at the work point or at where your probe tip would be. So now we're going to talk about the different types of errors and error motions and how we come up with these sort of specifications. One important concept is accuracy and repeatability. So every specification has an analogous accuracy and repeatability type spec. A good way and easy way to explain this is with the game of darts. So if you look at the dartboard on the far left-hand side, you'll see as you throw darts, they're kind of scattered around the board. In this case, if you're aiming for the bullseye, you can see we didn't hit the bullseye. There's a lot of error from what dart to the bullseye, and the distribution of spots where the darts would land is very wide. So this is not accurate or repeatable. If you look at the center plot, the distribution of darts is very compact, so this is a very repeatable scenario, but your average position of those darts has a large error between your average and the bullseye. And if you were aiming for the bullseye, you're repeatable, but you're not accurate. So to be accurate and repeatable is for the error itself between the final position and the desired position to be small, and for repeatability for that distribution to be nice and tight. So we'll keep referring to these as we go through. You see here two single axis stages. One's a linear stage, one's a rotary stage. These are typical stages that Aerotech would use in optical alignment type applications. We typically like to do serial stacks. We find that we can achieve very high positional accuracies and very fine resolutions with this. So we'll talk about these stages. In the direction of motion, a motion supplier would typically refer to an accuracy and a repeatability, just as we had just talked about. In our case, we would use in a linear stage a laser interferometer with an optic at the work point to measure the accuracy and repeatability and along the direction of travel. And for a rotary stage, we would use an autocollimator and a master axis to measure in the direction of travel. And essentially, we're doing just as we did with the dartboard. We're measuring the commanded position to the stage in the software, and then the physical actual position as measured by the external device. There are other errors as well in the other 5 degrees of freedom. So there's 2 other linear errors and 3 other rotational errors. It's important to understand that these exist, and they also have analogous, we'll call it accuracy and repeatability type numbers. So typically motion suppliers will show a straightness, a flatness, a yaw, pitch, and roll. Those we'll call an accuracy type number, meaning that it's a peak-to-peak number over a full travel in a typical scenario. You see analogous ones for the rotary stages over there. Now, motion suppliers should also know the repeatability of these errors. For example, if I move back and forth and move to the same point over and over, there will be some distribution to the vertical straightness that we can measure. And that would be the repeatability of the vertical straightness or the repeatability of the flatness. These are typically not posted on suppliers' websites. However, they should know these and be able to use them to estimate calibrated performance of stages. We'll talk a little bit more about this as we go into the case study toward the second half of the presentation and how this would affect your optical alignment. One thing that's important to note is whether or not your motion supplier guarantees a spec. This is how Aerotech is. If we tell you a spec, it will ship out with a spec, whether or not that spec is an average or whether or not that spec is like a 3 sigma distribution spec. These off-axis rotational errors are important, especially to understand, because they contribute to large errors at your work point. So if you look at the linear stage on the left-hand side, you'll see that expected position. This is the position that you would expect your optical probe to end up in. So let's say your optical probe is at that point. You make a linear move. You would expect to move along a line and potentially have an accuracy and repeatability error on that line. However, because there's an offset between your encoder, which is in the stage, and the physical probe position, which is at that expected position, this offset amplifies the angular errors. So if there's a roll or a pitch of the stage as you're moving in the direction of motion, that manifests as a translational error at the work point, amplified by the moment arm from the encoder read head to your probe position. So instead of ending at the expected position, you may end up at the actual position. This isn't necessarily an important thing to know for every application, but there are definitely points where this can significantly affect and potentially even make your application fail with your automation equipment. And this is what we're going to look at in this case study going forward is how do you determine what specifications are important? Typically with applications, there's 2 to 3 specifications that will make or break the application. So it's important to be able to take your process and to analyze your process in a way that converts your metrics into precision motion metrics. And so that's what we're going to do with this case study is we're going to talk about a typical optical alignment, and we are going to decompose it into motion specifications. I'm going to go through the typical process that I would go through with a customer as an applications engineer to give you an idea of how to approach choosing an automation system. Now, going through this case study, I'm not able to show any of my customer images or specific customer data because it's all protected under NDA. However, I'm able to show the types of specifications and general data that we've been able to collect and use to analyze these sort of applications. So we'll go from there. As I mentioned at the beginning of the presentation, a current trend is wanting to be able to do edge coupling at the wafer level in a trench. And typically those trenches are long and they can span the entire length of the wafer in some cases. So what you see on the left-hand side is a 6 degree of freedom direct drive cross roller bearing stage stack. This would be the optical aligner stack. So this would carry your probe that you would use to probe the wafer. On top of that stack, you'll see that arm, that silver arm, and that is holding the customer's probe. In this case, in that picture, it's an array probe probing a die. However, we're now moving into a time where people are trying to do edge coupling at the wafer level. So you'll see on the right-hand side a cheap sketch of what the cross-section might look like, where we have a trench and we have a fiber array that's going down into the trench. We want to be able to probe the edge coupling, the edge of that waveguide, and then move from one waveguide to another without exiting the trench. And the question is, if I want to automate this process, what specifications do I need to look at with the precision motion supplier? So this is how we're gonna break this down. The first thing that you need to be able to quantify is your optical sensitivity as an alignment tolerance. So there's 2 ways to do this. You could physically measure it, which I'll talk about here, or you can simulate it and come up with a number, typically in a tool like Optics Studio. In this case, this particular customer provided me with their optics, and we did this physical test, the results of which I'm showing here. They also simulated it at the same time and came up with a verifying set of data that verified our tests. So what you're seeing is a plot that has been generated from Aerotech software. It's basically our visualization software to visualize signals in your controller. The top plot that you'll see that's stepping up and stepping back down, that's the position command to a given axis, in this case, the Z-axis. And we are making 100 nanometer steps, 10 forward steps, and 10 reverse steps. This stage is very capable of making small steps, so we know that it can make these 100 nanometer steps with no problem. I'll prove that on the next slide here. The bottom plot is an analog voltage supplied by our customer's photodetector that is feeding into our controller's analog input. So we're able to plot these in the same plot. This represents the optical power. It is normalized, so we're looking at a normalized number here. And as you look at this, you see 2 peaks in that optical power. That peak happens to be about in the center of our move profile, going forward and going backward. And if you look at this, toward the top of the peak, you'll see that we make a step, we make another step, and there's a very slight change in the optical power to the point where the noise of the signal is starting to disrupt the ability to tell if we're increasing the optical power or decreasing the optical power. That, in our terms, is the optical sensitivity. So we now know, and we've correlated this optical sensitivity or alignment tolerance to a requirement of 100 nanometers. So I now need to select a automation equipment that can achieve 100 nanometer step sizes or smaller. So that is the first important specification for this application. Now, of course, you want to prove that your system can achieve those step sizes, and that's what we're showing here. So your automation supplier should be able to prove that either through data or estimates of their performance. What you see on the left side is that same stack. Our functional point, or your probe tip, is about 1 inch up and 3 inches out from the mounting position. And we physically measured this at that functional point, or at your probe tip location, using CAT probes. We took that bottom axis, commanded 10 nanometer steps, and you see the CAT probe output on the right-hand side in the plot. You'll see in that plot that first off, there is some noise. That noise is about plus or minus 3 nanometers or so, peak to peak. So you can see that the noise in the plot is smaller than the step size we're making the steps very resolvable. You can see that the steps are very consistent forward and backward. So this is an important thing. We'll talk about this in a second. It's analogous to a repeatability. And you can also see that we can achieve smaller than this 100 nanometer optical sensitivity requirement. And that's very important. Now we know this particular automation equipment is able to at least take step sizes that are smaller than resolvable by our optical system. So that's a good start. The second typical important specification is repeatability. So usually you're running some sort of algorithm and moving in 2, 3, 5, or 6 degrees of freedom on your stack. And as you do that, you're measuring and recording the position of the axes using their internal feedback, in this case, optical encoders. And you're typically measuring your objective function value, which is generated based on your optical power. You're corresponding these to different locations, and after you've completed your move profile, or as you're completing your algorithm, you're looking at what position is the optimum optical power. Whether you're looking at a minimum or maximum, it does not matter, right? And you want to be able to return to that position to within your alignment tolerance. So in this case, within 100 nanometers. That is a repeatability over the small area that you're aligning in. So if you're doing a surface coupling application, you may care about aligning within a plus or minus 10 micron window. If you're doing an edge coupling application, you might care about aligning to within a plus or minus 2 micron window. So it depends on your optical distribution. In this case, you can see that over our 100 nanometer steps, 10 forward and 10 back, the worst case repeatability is actually at the 0 position, which is not surprising because it's the longest distance traveled. You can see here that we start at 0 with about plus or minus 3 nanometers of noise, and we end at approximately negative 4 nanometers. So in this case, over our 100 nanometer distance, we have approximately a 4 nanometer bidirectional repeatability. This gives us confidence that not only can we resolve the optical sensitivity of the system, but we can also return to the optimum. Now, those are the typical important specifications for optical alignments: step size and repeatability. However, edge coupling in a trench adds another layer of complexity. First, you have this trench that's 10, 15, maybe 20 microns wide with some known depth, and you can't crash into the wafer as you move along it. And you have an optical distribution that you typically would like to do insertion angle alignments to. So you can't drift or have off-axis errors larger than, let's say, plus or minus 5 microns without losing your optical signal or crashing into the wafer. Your precision motion supplier should be able to estimate the errors at that work point. Remember, we talked about angular errors amplifying between the optical encoder and your probe tip, and I'm going to show you here how we can estimate this based on our data. So this is an example of the same stack, and we're measuring errors and we're estimating what they should be at the functional point, or at your probe tip. Linear errors translate directly. So a 1 micron straightness error will translate directly into a 1 micron straightness error at your probe tip. We can add these up for each axis in the stack and come up with an estimate of the total error. Angular errors, if you remember, are amplified over the moment arm. So here's an example of where this becomes a problem. If you look at the left-hand side, I'm showing this red arrow that shows the offset from the encoder, the optical encoder embedded in the stage, to the functional point, which is your probe tip. On this particular system, that's almost 230 millimeters, which is a large offset. And you're amplifying all of your angular errors over that distance. If we make estimates on this, you'll see in this what we call a functional point accuracy calculation in the center of the page. You'll see these numbers of 5.9, 5.9, 1.8. These numbers are a plus or minus peak-to-peak number in microns that represent the error that we estimate at your functional point over the full travel of the stage due to rotational error of the stage. So you see that just because we have a small rotational error and a large moment arm, we're estimating to see up to plus or minus 6 microns of error in the translational directions due to that moment arm and due to the angular errors of the stage. We can estimate these for each stage. So if you look at the y-axis, we can estimate these for the y-axis in the 3 different degrees of freedom. And as you look at this, you'll recognize that we have plus or minus 6 microns of error in the y-axis, plus or minus 7 microns of error in the z-axis, and we haven't talked about axes z, a, b, or c. So once we do this for the whole stack, we come up with a number that's somewhere between plus or minus 20 microns and plus or minus 30 microns. And this is too large. We would crash into the wafer, we'd crash into the side walls of the trench, and we would lose, as we're doing insertion angle alignment, we would lose the optical signal altogether. This is where you need to ask your precision motion supplier about their calibration capabilities. Typically, the accuracy is not that important in optical alignments. However, with this trench level optical alignment, the edge coupling at the wafer level in a trench, the accuracy is important because as you do a insertion angle adjustment, your linear axes are moving over larger travels, and this these directional errors are amplified at your work point. We can calibrate if we know the position of your probe with respect to the mounting surface. We can calibrate with our optic at that point and essentially remove most, if not all, of the error associated with the amplification over the moment arm. And that's what you're seeing here. You'll see on the left-hand side, the uncalibrated stage with plus or minus 7 microns of accuracy over the full travel. And on the right-hand side, the calibrated stage with an order of magnitude smaller, plus or minus 600 nanometers of accuracy at the probe tip. So we can account for all of or most of the moment arm error due to your probe tip offset to the optical encoder just by calibrating at that point. So at Aerotech, we're going to ask you where is your point of interest and what is your payload for this reason. You also want to be able to optimize your insertion angle without all of this XYZ error. We talked about how we can calibrate the stack to get rid of the error, but there's also error associated in your measurement of the offset. We have to run everything through transformations, and you have to know where's your rotation point versus the stage rotation point. You can measure this in CAD, but at these micron levels that we're talking about, the tolerances of the assembly and the machining become a problem. You can actually use external feedback to compensate for this, similar to the calibration we've shown before. So if you look at this image in the center of the screen, this is from my microscope camera. You'll see this fiber here. This is a 9 micron fiber, single mode for telecoms wavelength. And you see us making about a 4 or 5 degree rotation in the yaw. Now the tip of this fiber is at our functional point, 1 inch up and 3 inches over. We can use these cameras to measure the offset during a known rotation and to optimize where we think the position of the tip of this fiber is. On the right-hand side, this is the result after we've run the optimization. And you now know that you can achieve approximately down to that number we came up with in that last slide at this tip. Now, when you add that up for every axis, that becomes a number like plus or minus 5 microns instead of a number like plus or minus 20 to 30 microns. You'll see in this image over on the right-hand side, we're actually constrained by the resolution of our microscope cameras, which in this case was about 2 microns. So you see a little bit of drift there just due to the constraint of the camera resolution. Lastly, you do want to make sure that your precision motion supplier is able to take your photodetector signals and feed them into the algorithms or the feedback loop. So at Aerotech, we were able to do that. you can do 1 to n photodetectors and define your objective function in any way you wish. All right, I'm going to end this with showing you an example of an actual optical alignment using all of these things we've talked about. You see up in the upper left-hand corner, there's these two 6-axis stage stacks. They're the same stacks we talked about before. The offset's approximately 1 inch up and 3 inches over, as we talked. You'll see in the downward-looking camera that we have 2 fibers. The fiber on the bottom is that single mode fiber that we calibrated the pivot point for. That is the source. Fiber on the top is a single mode fiber that we calibrated the pivot point for using those cameras. That is connected to the photodetector. And in between, we have this glass substrate. So I'd like to say thank you to our friends at OptoScribe. They provided this substrate for us for this testing. This substrate contains 12 waveguides in clusters of 4. You'll see the schematic on the right-hand side of the screen. So the center ones are straight and the ones on the left and right are tapered. So we're going to go ahead and we're going to perform an optical alignment here. You'll see the optical power measured from the analog voltage at the bottom of the screen here as the optimization goes. Keep in mind, this particular stack is not calibrated, so we expect, as we've done, plus or minus 20 to 30 microns of error over large travel moves. So I'm going to play this video and we'll see this thing happening. So we've used the camera to identify the tip of the fiber and to identify the fiducial on the glass substrate. We've then commanded this thing to move in, and as it moves in, you see that the optical power rises. Then you're going to see this series of the 4 alignments to the center waveguides. Then you're going to see it make a move to the waveguides on the left-hand side. We're currently using the pivot point functionality with our optical alignment algorithms to align both the input and output simultaneously through contoured motion. And here you'll see it's going to make the longest move, the full length of the substrate. And as I mentioned, this is not calibrated, so we expect a larger error at our tool point or at our tip of our fiber, as we mentioned. And you'll see that strange shape in the power plot at the bottom of the screen. That's because we actually couldn't find the optical profile initially and had to search for it due to that accuracy. So if these stages were calibrated, we would have found the optical profile immediately. I hope this presentation was helpful to you. Just to recap, the important things are being able to take your application and breaking it down into the 2 or 3 specifications that are most important for application success. In most optical alignments, that's going to be small step sizes and the repeatability of the stages over your optical alignment area. So you'll need to know your optical sensitivity, and you'll need to know the size of your optical distribution. For some of these more advanced alignments, like edge coupling at the wafer level in a trench, we might also need to take into account other errors during insertion loss or insertion angle optimizations so that you don't crash into your wafer. Or if you're doing something, let's say traversing the full wafer in the trench, the straightness, flatness of the full stack so that you don't crash into your wafer during this. Thanks for your attention, and let us know if you have any questions.
Thank you very much. Everyone, if you have not already, please go ahead and type your questions and comments into that webinar chat. Aerotech's team will be following up with these questions by email after today's event. If you do think of another question, you can let us know by emailing webinar@photonics.com. That's webinar@photonics.com. And just one final note, this whole session was recorded. It will be available on the Photonics Media website shortly, and you will receive a link to that recording by email. So I'd like to thank Brett Heintz from Aerotech one last time, and thank all of you for participating today. This webinar was presented by Aerotech and hosted by Photonics Media. Thank you, everybody.